Hello, everyone. I'm Dave Moffat. I'm one of the committee members for AES UK, and I'm here to introduce Josh Reiss. So Josh Reiss is a professor at the Centre for Digital Music at Queen Mary University of London. He's been heavily involved in the AES for many, many years, and as of the start of this month, has recently become the president of the AES as well. So we're very honoured to have him here. I believe giving your first talk as AES president. Is that correct, Josh?
Yes, that's correct.
Great. So in which case, I shall stop sharing and hand over to you, if that's okay.
Okay, yep. Thanks a lot, Dave. And I'll say a few words about Dave, who just introduced me. He did a fantastic PhD with a mediocre PhD supervisor, myself, and Dave's career has been all downhill from there. No, quite the opposite. But thanks for the introductions, Dave and Neil. Very much appreciate it. And thanks for inviting me to give this talk today. As you can imagine, I am very excited about the AES, very proud to be a member, to be a fellow, and now to be president. And I'm also especially excited about the upcoming 152nd AES convention in The Hague in May. I think since COVID began, it's the first major AES event expected to have an in-person presence, as well as the online component as well. So with luck, I'll be able to see a lot of you at the event. So today I'm going to talk about a subject titled Procedural Audio Worlds, and it's based on research that's been done by my research group for many years and has led to a spin-off company. So I'll give you a little bit more detail about myself. Basically, have had a 20-year research career, and a lot of the research that I've been involved in, it was never the original intention, but it's been commercialized. And so I've become, by accident, a bit of an entrepreneur. The first company I was involved in was based around the idea of automatic mixing. Can we get computers to mix audio to a sufficient quality, not that they replace the sound engineer, but that they can provide presets, make the job easier, and create a decent mix for those people who, or those situations where there isn't access to a professional mixing engineer. And that company evolved over time and transformed into Lander, which most of you have probably heard of by now. Also involved in another company, smaller but still founding role, called Tones, which is delivering audio effects based on deep learning techniques. And the third company, I'll be talking about the research behind that company today. The company is Nemisindo, and it delivers procedural audio technology and sound design services based around that technology. But this is not really intended as a promotional talk. It's to explain the research questions and the research in the area, both from my group and others, what it's all about and what are the directions for the future, and how it may revolutionize many aspects of sound design. So without further ado, I shall begin. So the title of the talk, Nemisindo, Procedural Audio Worlds. And let's see. Okay, so in sound design for games, film, and TV, the sound design is done usually via two well-known techniques. The first of them is Foley sound design, which is basically banging pots and pans together and sticking a microphone next to it. Now, it's an art form. It's a lot more than that, and the Foley sound designers are true artists. But what's interesting is that the field has changed very little in 80 years. The difference between the photos on the left, and I know that the top left photo is Foley sound design from the movie Dumbo, which I think was around 1940, versus the Foley sound design being done today. The biggest difference is that the photos on the left are in black and white, and on the right, they're in color. And there's now women doing sound design. But the technique, the Foley technique, really hasn't changed over all that time. The alternative to that is working with sound effects libraries. So vast quantities of pre-recorded sounds, and one uses those sounds in their creative content by finding the sound that is closest to what they want and performing additional processing and manipulation and editing of those sounds. The problem with this technique is it's very uncreative. It's always someone else's idea of the type of sound you might like. You want the sound of an alien monster, go search through the library for lion roaring sounds and similar sounds and modify it until it sounds good. That's not a creative way to work. Every sound designer, they want to be out recording and creating their own sounds. It also means that the sound effects can be repetitive. You might end up using the same sound over and over. You might end up using the same sounds that other people have used unintentionally. So it's not the desired way to work. But contrast that with what happens with video effects. So digital video effects have reached an incredible level of quality, so much so that they're almost indistinguishable from reality. And those video effects are created digitally and in software. But they don't do the equivalent of working with sample libraries. They're not based on trawling through thousands and thousands of photos in a collection to find the closest photo. So it brings up the obvious question, why can't we do in audio what they are doing so effectively in video? And the idea there is what is known, at least in the game sound community, as procedural audio. It represents a disruptive innovation, a new way of doing sound design. So many of you might be familiar with procedural audio, or you might be familiar with sound synthesis, which is this general idea of creating sounds algorithmically or from different components, but not based entirely on just using a recording. It is like sound synthesis, but it also has the requirement for procedural audio that it needs to be real time and adapt to changing inputs and parameters. So think of the sound effects as methods, not samples, like working with a recipe rather than buying a ready cooked meal or just putting something in the microwave. It might be more effort, you might be some challenges in deciding what to do with the recipe, but ultimately it should yield better, more interesting cuisine. A few of the advantages of working with procedural audio over working with samples includes the idea that you could produce a whole range of sounds. If you have footsteps, you should be able to have a model where you can arbitrarily change the speed at which someone is walking, rather than finding a sample for a slow walk, a faster walk, a jogging pace, a sprinting pace, and so on. And the sounds can play for any amount of time. So again, since he introduced me, I'm reminded of one time I was talking with Dave a few years ago, and Dave has a background doing theater sound design. And I said to him, this area of research, I don't think it has many applications to theater sound. And Dave pointed out, oh, it very much does, because there will be situations in theater where someone perhaps might need to be talking over a thunderstorm in the background. But actors will change their lines. They might say something slower or faster and run over. And you don't want to have just a single sample looped over time. You want it to sound natural and be playable for any amount of time you want. They can also have intuitive control. So a well-designed model, you can again specify speed at which someone is walking or making an explosion boomy, or how angry something should sound. And you can create sounds that have never existed in nature, unreal sounds or imaginary sounds. So I think I have a sound example here. So the lightsaber sound from the original Star Wars movies, the prequels, I think, that was created by sound designer Ben Burt, making interesting sounds from the lighting on set. But the sound sample played just then was based on procedural audio. So, and in both cases, the sounds are imagined. There's no real lightsabers making the actual sounds that associate with the movie. So in that sense, procedural audio is much more like Foley than working with samples. In both cases, you're creating the sound in some sense. This changes how sound is done. Films and games, the work of the sound designer in these creative industries would completely change if they're working with procedural audio in an entirety. It allows them to take control of the sounds and create new sonic experiences. But it is a very different way to work, and it's very challenging to ask a professional sound designer who's become expert in one approach to suddenly try taking a different approach. It's also a difficult thing to introduce to the market, because if you take some content, say a game, and introduce one procedural sound in there and the rest is samples, you've actually made the sound design work more difficult. They're now working with two different approaches. They need to integrate two different ways of doing things. So you only really start to see the benefits when there's a lot of procedural audio. And we'll talk about that more in a few minutes. So that was the challenge that we were interested in a few years ago. And not just can you create these procedural audio models and sounds, but could they actually do the job that the sound effects library does? And working with a sound designer / PhD student, Simon Hendry, we started exploring just this question. So he took some sound samples from the BBC sound effects library and thought, can I also start with a procedural model of similar sounds and reach an equivalent level of quality? And can I vary the parameters of those models such that the sounds that I create match, or a close match at least, to the sounds in the sound effect library? And so this is a result of his work, and it is very close to a recorded sample. So the work went great for a while, and we started building more and more models. We were taking ideas from many different places. The main emphasis of the work, and what tried to distinguish our approach from others, is that rather than trying to create, say, the best physical model of one particular well-known sound, which we are still interested in, we thought, can we create such a wide range of models of sounds and make them so usable that it can actually do away with the other approaches? And this was funded by Innovate UK Research, which supports commercialization. We thought there could be a business model here, and it led to the founding of a company called Nemisindo that have all of these sound design models available for use and provides tools for the sound designers. So to give you an idea of where we're going with this, I'm going to play this short video here about Nemisindo, what it's trying to do, and the underlying technology. So that's the idea. That what we're trying to achieve, if it works, can allow all of the objects in a virtual world to interact and produce the sounds for their interaction. You can imagine a virtual reality scenario. Most of the time now, it's still based on samples. And so there's a limited number of samples that can be used in a VR setting. So you can't really develop the rich and diverse range of sounds that one could have in an auditory world. The aim, the vision, is to be able to achieve all the sounds in a scenario. But that's the top level view. Let's dive into the details and the research questions involved. So we have an online system showing off what's happening, and it does at least try to do all of what we're talking about here. How does it work? All of the sounds created within this online system are based on a very modular approach where we have individual models for sounds. So taking nature sounds, wind, rain, thunder, and stream, they can be combined together to create a storm sound. And they are combined in parallel, and then audio effects applied in series on top of that, reverb, compression, and mastering. The overall system that one can use works a lot like a DAW, mixing the sound effects together to produce the desired sound. Another view of the architecture is like this. One can browse by model, so looking for wind sounds or stormy sounds, or one can enter a preset, the sound of a Bunsen burner flame or a candle sound. Then there's an algorithm, the audio signal processing algorithm, which is built into a plugin, what's known as a JavaScript audio plugin, something like a VST plugin, but designed to work on the web. And the combination of them plus effects like spatialization is then rendered for the output sound. This architecture for the online system that's being described, it's all browser-based. So there's no server-side processing, there's no heavy computation in the background, and that's part of the challenges of developing it, to make the whole thing lightweight while at the same time working real-time. To achieve this, we make heavy use of the Web Audio API, and especially audio worklets, which allow any sort of audio processing to be done within the browser. We also used JSAP, as mentioned, the JavaScript audio plugin format, developed primarily by Nick Gillings and others at Birmingham City University. And the Nexus user interface, which provides an audio style DAW and mixing console style interface for web applications. So these models of sound, I've talked several times about trying to create all of the sounds. So how are they classified? And if you read sound synthesis papers and procedural audio papers, they often start with a sort of classification of the field. It's actually quite a hard thing to do, and people have looked into ecological classifications of sounds, non-signal processing based approaches, and more for many years. So quite loosely, the sound effects that we're dealing with can be classified as shown. You could classify them by sort of sound classes, those that are animal sounds, science fiction sounds, aeroacoustic sounds like propellers or swinging a sword, and mechanical sounds and contraptions. Like the sci-fi sounds, there's also artificial sounds that can be simply constructed: alarms, ringtones, and beep sounds. Or impact sounds, so a simple impact of one object against another object producing a resonance like a gunshot. Textures, these are formally defined as sounds that have constant statistical properties. So if a rainstorm were to last forever, it doesn't matter whether you listen to it now or an hour from now. If you were to take a sufficiently long segment, extract a lot of features from that segment, you would have roughly the same values regardless of the time of the sound. You could also classify these sound effect models by the type of control that is applied. So there are certain sounds, mostly the impact sounds, that just have a single trigger. So a rocket launching, a ball bouncing, or a spray can being pressed. Or sounds that one starts and stops, so footsteps starting and stopping. Other sounds, like the sound of wind and most of the sound textures that were mentioned, are continuous. They just run in the background all of the time. They can be controlled and modified, but you don't necessarily start and stop the sound for realism. Some of the models are keyboard-based. Some are based on the movement of a control, and it's that movement that produces the sound. So moving a slider back and forth to produce the sound of a creaking door, or moving your mouse back and forth to create a friction or a scraping sound. And finally, the sound models that we've been trying to produce for this procedural audio world could be classified by the synthesis technique. So this includes physical modeling approaches, where one tries to essentially synthesize or simulate the sound producing mechanism, and the sound itself is just a byproduct of that mechanism. Or signal-based modeling, which is often, it can be inspired by the physics, it can look at the physics, but ultimately it's manipulation and algorithms to modify and process and generate sounds, regardless of whether they match the physics, as long as it matches the signal that should result. Within that field, we have additive synthesis techniques, subtractive synthesis techniques, and more abstract techniques based on audio effects like FM and AM synthesis, or else, especially when not directly related to the physics, techniques like the Karplus-Strong algorithm. Some of the models that we've been looking at are hybrid approaches. So when we started work on the research question of can one procedurally generate all sorts of sound effects, we thought, well, okay, what approach should we take? And there are very general approaches. There are things like sinusoidal models or deep learning neural networks, which I'll talk about a bit later on. But we started it off with a lot of small projects, which meant we couldn't necessarily build a big team to do several years of research and hope for a strong outcome at the end. Rather, we thought, well, let's look at the work that's out there. So much research has been published in places like Audio Engineering Society conventions and conferences and the Digital Audio Effects Conference Series, that maybe we can re-implement many of those techniques, and techniques that are in the public domain, or techniques that have been contributed by great researchers like Andy Farnell. See if we can pull them all together, improve them, modify them, and see if collectively that allows us to cover the rich range of sounds one finds in a professional sound effects library. That also meant that many of our models are hybrid approaches. We might take techniques from physical modeling, but supplement them with signal-based modeling to improve the quality or modify the controls and so on and so forth. So in all of these cases, we start with a model, but then we fine-tune the parameters as much as we can to match recordings or just based on insight that we know about. Another example is some of the abstract sounds that we work with, like the sound of whoosh. There is no definitive whoosh recording, but people generally know what they mean by whoosh, and there are examples that are close to it. So we inform that model by prior knowledge of what we think it should sound like, or what sound designers have told us. So to give you an idea of a few of the sounds generated by these models, and I do hope the sound is quite good for you over Zoom. Physical model, we had some research mainly by Rod Selfridge to do with aeroacoustic sounds being modeled both physically and procedurally. And here's the sound of a golf club swing. And additive synthesis techniques like the sinusoidal model have been used, where we essentially construct the sound by adding together lots of sine waves or wavetable synthesis, so lots of some waveform, some excerpt that can be built up from there to generate the sound. With our approach, we are not storing rich sound samples. So we're not taking a granular synthesis approach. The additive synthesis approach that we are taking, we are still encoding a very, very small amount of information to generate much richer sounds. So this is a model that I worked on where I looked at a recording of Big Ben, which was very appropriate at the time because they just started work on renovating Big Ben, so you couldn't hear it live anymore. So worked on a recording, extracting the dominant frequencies and the decay rates and other attributes, and used that to construct essentially a sinusoidal model of the recording. Now, it probably didn't come over that well. I think listening to this sample on its own over headphones, you would hear a lot more of the sound. But as a small anecdote, when I worked on this, I thought I had made a mistake because when I listened to this result, I actually thought, well, I just played back the original recording by mistake. And then listening carefully, I realized it was a very good model. And it's one of the rare times in my life where something I've coded worked just right first time. I assumed I must have made some silly mistake because it had sounded so close to what I hoped it would sound like, but it had actually worked just fine. Another approach we take, and perhaps more than most approaches, is subtractive synthesis. Subtractive synthesis usually starts with a very rich signal, and one applies EQ, lots of filtering to carve and shape the spectrum of the signal, and applies envelopes to shape the signal in the time domain and shape its envelope on both small and large scales, and other types of processing to go from an overly rich signal to a signal that sounds like what you want. So here's a small example of some very dense ocean waves. And the third type of signal processing that we heavily use is using techniques like FM and AM synthesis. I should mention, so FM synthesis was created by John Chowning and others somewhat serendipitously at the Stanford University in California, playing around with different ways to manipulate sounds, and started realizing that they were creating some really interesting and useful sounds for synthesis here, and only later were able to look back at what they'd done and realize how to explain it mathematically. But it really just involves modulating the parameters of sine waves or other simple oscillators. So a lot of the techniques come from manipulating basic sound sources and being able to achieve something very rich. And it's quite interesting and tells you a lot about how much can be done just by manipulating sounds. So the world of sound around us is very rich, but much of that is due to spatial aspects and due to the fact that sounds are composite. To actually create a sound that sounds somewhat close to a target, sometimes you can start from something quite simple. Now, it needs a tremendous amount of refinement to get just right, but you can achieve so much starting from a small amount. And it's one of the reasons why these procedural models can work, and yet the model itself can be very, very small. And yet that small model can replace much far larger recorded samples. And here I'm referring to size in terms of the actual amount of file storage it takes. So that's the idea of where we're coming from. I'll play for you this model based on FM and AM synthesis, and it is essentially how police sirens do work. Now, of course, you're familiar with hearing police sirens, but what you also hear is you hear police siren generally not out of loudspeakers, with lots of other sounds going on in the background, often the sounds of traffic, so sounds that are keynote sounds and sound marks that tell you where, and they give you something of the setting and they're fairly iconic. And you also have natural reverb on it. So one of the things we've found is that the sound models will often sound unnatural, but it's not because of a problem. It's more because we're not used to hearing a sort of pristine sound in the equivalent of an anechoic chamber. We're used to hearing it in a much more real setting. So while models often do have problems, not all of the problems or all of the artifacts and perceptual differences are attributable to the model itself. I'll also note that with a lot of this research, we were talking with sound designers throughout the research, and they told us the police siren model that we have is good, but there needs to be a lot more. And the real issue is that people all know what their local police sirens and ambulance sirens sound like, but they're different. They're different in every country and even state by state within the US. And film sound designers have to be very careful that, for instance, if they have a scene set with a car chase in New York, it needs to be using New York police sirens, and they need to sound right. So we then took our model and found the parameters associated with the different sirens of different locations and added them all in as presets to the model. So that's the idea, that's the ambition, that's where we've been taking it in terms of commercialization and our attempts at innovation. But there are real challenges here that require not just engineering effort and development, but long-term sustained quality research. So the big question that everyone always has, and a very legitimate question with any procedural audio model, is how close is it to the real thing? No one wants in their sound design for people to walk out of a cinema or something like that saying that explosion didn't sound right, didn't sound like an explosion. It's been said before that people almost never will walk out of the cinema saying that movie sounded great, but they will sometimes walk out of the cinema saying that movie sounded really bad. Sound design is often not noticed if it's very good, they just enjoy the movie, but it is noticed when it's a problem, and that certainly needs to be avoided. Anyway, so we have been looking at the sound quality of our models, and here are two examples. On the left, we've been looking at our applause model, which is informed by physics and knowledge of applause, but is very much signal-based. And some interesting things went into it. For instance, it's based on some research where someone put a huge amount of effort into analyzing how people clap their hands. And they found that there's something like 7 different forms of putting your hands together for a hand clap. They can be flat against flat, or just the palms connecting, and so on. All of that research informed the model that we developed, and we compared our model against 4 other forms of sound synthesis and real-world recording. And we've got very, very close to the real world recording. When we asked people what were the differences they noticed, for the few people who did notice differences, one of them or a couple of them reported they could hear someone coughing in the background. Someone else said they could hear stamping feet. In both of those cases, those were in the real world recording, but not in our simulation. We were just getting the sound of applause. So there was no way this model would have been a perfect match. But it's clear there that the approach that we were taking showed that a procedural audio model could get very close, perhaps even indistinguishable from the real thing. But that wasn't the case with thunder. Thunder is very interesting just for what it is, but also that there is some really great classic research on trying to recreate the sound of thunder. And I wish these people were around today, because there's a well-known paper in the field of thunder and lightning research from about 1980, not an AES paper, where the authors describe in detail their physical model of thunder. And they produced recordings of it and said, when we demonstrated these recordings, people said it was very good. Despite far too much effort, I could not find any of those recordings, anyone whose work is based on those recordings, who had a good sounding model. And my attempts to reproduce the sound based on their paper didn't sound any good at all. So although there's been a lot of research on this, it's still very much an open question. So I think it was just over a year ago, we published at an AES convention a comparative evaluation of all of the different thunder techniques that we could find. And some of them are shown in this plot here, where the recording is the first one. One at the top of the scale would indicate that that everyone said it was completely realistic. A 0 would be everyone rating it as unrealistic as possible. The Blanco technique is based on that famous paper that I mentioned, but I think there might have been some issues with the implementation of the code that the authors provided. The other techniques, Farnell's model is a procedural model. The Max model is somewhat similar to Farnell's. Saxella is based on a completely different physical modeling approach, an interesting one, but not informed by that same paper I mentioned. The effective model is our first attempt at creating a thunder model, and it's also loosely based on Andy Farnell's work. And even though it's based on Andy Farnell's and was an attempt to improve on it, it performed worse. But also in this test, we found none of the models, even the ones that claimed to be good, were any good. So there are phenomena, especially natural phenomena that we're very attuned to, that no procedural audio model so far can get quite right. And I really started paying attention to this a few months ago, when there was a thunderstorm here in London, and there was a lightning strike, probably no more than 5 meters from where I was at the time. And it made me focus on the sound of thunder and how many characteristics there are of the sound and subtleties that none of these models get, but they possibly could get. So getting the crackling sound before the thunder strike should not be that difficult. Getting the spatial characteristics of the sound bouncing around you, certainly achievable with spatial audio tools and correct application of HRTFs for each segment of the lightning strike and so on. It's a model where there's vast room for improvement, and we'll be publishing a paper, hopefully, if it's accepted, at the next AES convention on an improved thunder model, where we did a new listening test, and it still needs work, but got a lot closer to the original recording than any of the models shown here. So this is an example of the fact that some sound synthesis procedural models sound very good, but some do not. And for the ones that do not, there are directions for improvement, which I'll talk about more in a minute. What we want is to reach a very high level of quality so that we have models that can run in real time, models that can sound like the real thing, models that can be controlled, whether within, say, a game audio engine or by a sound engineer manipulating the model the same way that they would do Foley design. And we want those models to be at a level of quality and richness and usability such that they can be out in the marketplace and they can be a tool that makes the job of sound designers more enjoyable and easier. So I'll play a short video here showcasing one of our models that I think is pretty good, which is based or trying to create the sounds of different automotive engines. Here we go. So I mentioned that none of the other models, at least for that none of the models for Thunder sounded that good, and that for the applause sound, none of the other models sounded that good. And when we have performed tests, they've all been like that, that we've found that very few models sound good. Modern research, so research in a lot of fields has been revolutionized in the past 6 years or so with deep learning. Before then, people started realizing that the deep learning techniques were effective. And then for certain problems like facial recognition, where there's a large community all trying to get an increase in improvement and no one was getting it, suddenly someone presented a deep learning neural network paper where the state of the art was 85% and they would get 88%. And it was a breakthrough. And they were finding in so many different fields that these sorts of breakthroughs occurring, not just things like facial recognition, but AI-based medical diagnosis. So it changed the field. And a lot of researchers now think whatever the problem, just apply deep learning, apply a large enough neural network with enough computation, and it will solve the problem. But I want to emphasize this to the researchers out there. Deep learning, it is wonderful, but it's not a magic cure-all for everything. So here's a few reasons why it is not the easy solution here. And let me step back for a second and say there are researchers working with me who are applying deep learning to similar problems, and they are getting very, very realistic footsteps or very realistic nature sounds like wind and fire, but it still isn't a solution for everything. Training data requirements for deep learning are often huge, but that data is not always around. If you want a particular sound, there might not be a lot of it out there. And that data still needs to be clean, it needs to be processed, it needs to be labeled. Even though there are tools sometimes that automate that, there's then more effort, manual effort by the researchers and the engineers involved. We also want the models to go beyond existing training data. We want to be able to create the sound of a dragon roaring. Well, no one has ever recorded an actual dragon roaring. And I did attend a talk one time by the sound designer on the Hobbit movies, and he talked about how he created the sound of smog, and he actually recorded alligators bellowing during mating season and applied a lot of audio effects on top of that sound. Well, it's a wonderful thing that he did, but how many people out there actually have the opportunity to do high quality recordings of alligators bellowing and apply all of the appropriate effects on top of that? Another great thing about when I attended that talk is the night before, we had just added an alligator sound preset to one of our models, and it was actually based on our understanding, our listening to the recordings that he ended up playing back again in his talk. So it was just a little bit of a surprise. Anyway, the models for procedural audio, they need to run real time. It's possible to create a model that runs real time with deep learning, but it's still a challenge. And they need to have intuitive controls. So how do you, in a very abstract neural network approach, create something that can say, I want to increase the crackling in a fire, or I want to change the wind speed, or change the number of blades on a propeller, or make this sound brighter or warmer, whatever is the appropriate intuitive control. Most neural networks act a bit like a black box, and it's very difficult to design one that is actually linked to perceptually relevant parameters. Different sound effects have very different requirements for rendering. So even if you find an approach that can translate to a neural network approach, then the next sound that you try to model will have entirely different requirements. So a one-size-fits-all approach probably won't work here. Yet despite all of this, there is a role, and a very important role, for machine learning and deep learning within the field of procedural audio and sound synthesis in general. So going back to Nemisindo for a second, we have about 75 different sound models in the system. They're all at varying levels of quality. But we also have a resource that we can use to improve them. We actually have great training data that we can use, and that's the sound effect libraries themselves. Those are all curated, high quality recordings, usually what the sound designers think are archetypal or iconic sounds, and most likely to be used by other sound designers. So we can use that as training data. We want to create the sound of rain. Here's 100 rain samples. We want to create the sound of a shower instead of rain. We have 50 shower recordings within our library. We can extract features and attributes from those sounds and try to take an existing model and modify that model, vary the parameters based on something like a gradient descent from neural network research, use gradient descent until that model produces sounds that are hopefully perceptually similar to the recordings. And in that way, the models that we've been working with, we may actually be able to learn the models and learn the parameters, learn the right settings to match a particular recording, and also do things like improve the model. If we have 5 models for rain sounds, which model is going to sound closest to the real thing? The effectiveness of deep learning approaches to optimize parameter settings tells us which model works well. We can vary how the model works internally, and again apply machine learning to identify which variations are most effective. We can then use techniques like active and transfer learning to learn the controls. So if we need a brightness control, play examples for listeners. Does this sound brighter? Does that sound brighter? Based on what they say, modify the internal parameters of the model so that we can find how to map parameters in the model to a perceptually relevant control on the interface. And the best way to do all these things is going to be with machine learning approaches. This is asking too much of direct manual control, but it should greatly improve the quality of what we're doing. We should also be able in future to crowdsource a lot of information. So for all of the models in Nemisindo, the presets have been hand labeled. We have decided, okay, we need the sound of a roaring fire. We need the sound of fireworks. We need the sound of a Cessna propeller or of a small drone. But if there's a community of users using these sounds, then they can say things like, oh, I've created something that sounds like bees buzzing. And they can share not just the recording, but share the recipe, share the settings on the model that will generate that sound. Or other people can say, oh, that sounds like keys jangling. And so someone else can label your sound. And we can use a crowdsourcing approach to show that this aim is being achieved, to show that we can create all the sounds of an auditory world around us. So crowdsourcing will definitely address some of the challenges. And one more problem is integration. So we have an online service, but the problem there is that the strongest use case for procedural audio is game sounds, because games are a nonlinear medium needing lots of sound effects. So you would like the sounds to adapt to whatever is happening in the game. But an online service, what can you do with the sounds? Well, you can record them, and then you can take those recordings, download them, and put them into a DAW or a game audio engine as sound assets. But that's no good. You might have generated the sound procedurally, but you're still using a sample. So we need to take these approaches and make them available as plugins for game engines. And we've started doing that. A few weeks ago, we released what we're calling the Action Pack for the Unreal game engine, one of the two most popular game engines. And so the Action Pack features about 9 of our different sound models, all related to action, like helicopter sounds and propeller sounds and gunshots and sirens. And we're going to deliver an equivalent pack for Unity and also a very detailed footsteps plugin coming soon for, mistake here, it should have said Unreal on the slide. So slowly, we're getting all of our models that are available online so that they can be integrated into game engines, and we'll be releasing VST versions and so on. Because this is not a research challenge, but it's a challenge nonetheless. If you have a technology based on a different way of doing things, it's a real battle to get people to adopt it. You need to make it as easy as possible to integrate your approach into what they're doing. And so the battle is not won once you prove a research concept. The battle is, to some extent, won once you get the community to adopt it. So at this point, I should start concluding the talk. I think we have shown that the potential is there, that procedural audio can be used as an alternative to sound effect libraries. And we may one day reach a point where we can procedurally generate all of the sounds in a sound effect library and more. The quality of the sounds being produced, the diversity, the range of sounds being produced, and how a sound designer can control them, or how it can be controlled within a game, are all improving. We're heading towards a situation where we can create virtual environments, procedural audio worlds, where every sound is procedurally generated. What might the world sound like in those cases? What might monsters and mythical creatures sound like? Alien environments, which can be generated graphically, what would be the sounds of those environments? So we don't know yet, but hopefully one day soon we will. And at that point, I would like to thank you once again. Obnoxiously, apologies, give another plug for our technology and the spin out. And point point out that all the sounds in this talk, except my own voice, were procedurally generated, no pre-recorded sound effects, and one more procedurally generated sound for you right now. Okay, thanks very much.
Thank you very much, Josh. That was a very interesting talk, and I very much enjoyed it. And the advantage of the sound of applause helps make it a bit better when we're working with online talks.